Hello, good afternoon. Welcome, thanks for being here. Can everybody hear me okay? Everything sound all right? Great. My name's Graham Boyd, Regional Manager with SLM Solutions North America. You'll have to forgive me a little bit if I pause or what have you. I had a 6-hour delayed flight last night, so I got in about 3 a.m. So if I launch into full-blown stand-up, you'll know why. So congratulations, you'll be my first audience here. So topic today is Hitchhiker's Guide to Metal Additive Manufacturing, the haves and have-nots to evaluate additive made parts. This is going to be pretty general. We're not going to get too technical here, but I figured this would be just good to give some exposures to some key topics and ideas, thoughts surrounding metal additive manufacturing. So diving in just to establish some credibility, kind of talk briefly about who SLM is. SLM Solutions is a powder bed fusion machine provider based here in North America out of Wixom, Michigan, globally headquartered in Lübeck, Germany. About 330 employees worldwide. We should be at about 100 million euros this year, and really our focus is high throughput production class technology. We do that through multiple lasers, open system. We have an open architecture, so materials and parameters are all open to those who work with us, as well as safety is a key differentiator or point to our technology in that we have a closed loop powder handling system, so less exposure to contaminant powders, operators, excuse me. Just a little bit about our history. The company actually dates back to the late 19th century, but really got into this whole thing of additive manufacturing and rapid prototyping in the 70s. And really the SLM technology was invented by our Chief Innovation Officer Scientist, Dr. Dieter Schwarze, back in the mid-90s. And then I say from the mid-90s to early 2000s, really when we did a lot of the R&D work that then led to the commercialization of the product that you see here with our 125 and 280 that were introduced in 2011, and our 500 where we have both a dual and quad laser 500 machine, which was introduced in 2013. What's next? Obviously everyone wants bigger and faster. Certainly we want to play in that as well, but you know, a big piece as it relates to metal additive or specifically selective laser melting is gas flow. So that becomes a real challenge when it comes to scaling things. And that is where folks are moving with production of metal-made parts. Beyond that, there's also software peripherals to verify and qualify additive-made parts. Lots of things happening. It's an emerging place. We're excited to be in it. And yeah, that's about all I have to say. About me, again, regional manager for the Northeast. I cover everywhere from Virginia on all the way through Pennsylvania on up into Canada. Been in technology sales for a better part of 15 years, and I have a liberal arts background by way of education, which makes me completely qualified to stand up here. Because for those who have ever made anything additively, sometimes you need a little religion and philosophy in making these parts. I think we've had enough looking at me. There we go. Today, you know, so the whole Hitchhiker theme, you can look at these as like planetary entities or something like that. But really, I want to talk about some key ideals or thoughts, like I said, when approaching metal additive manufacturing. Applications is the biggest, and it's in red there because that's the real main driver to looking at the end use case for additive made parts. That's where customers typically say, this is where we're going to start. You know, if what are we going to make is 50% of the product of product development, the other 50 is then materials, which is what are we going to make this out of, or how are we going to make this? And so that's really another big piece in this. We as well then have the machines, and there's various technologies. You've probably seen them many here on the show floor, from powder bed fusion, direct energy deposition, electric beam melting, binder jet. There's lots of different options. And again, all those talk back to the application or use cases. mix in some process controls and best practices. You know, we have lots of folks taking metal additive to production, and that's really where the secret sauce lies in getting things to production, is in those best practices and process controls, those who have had expertise and experience in making metal additive parts. This all equates to, oh boy, wrong way. This all really equates to the value of why do this at all? And I'm sure that's a question many of you ask. You know, lots of folks, as it relates to conventional manufacturing, have really know how to make great parts. And so you got to approach things with all these things considered to really drive the value and ROI in adding this technology. For those Hitchhikers fans, don't panic. There's both a direct and an indirect approach. We see, it's been our experience with with our customers and those that are adding this technology. There are folks that are taking a direct approach where they're setting out to address a problem or address a need with additive in mind, meaning they're going to design the part for additive manufacturing. They're going to consider the materials that they're going to use for taking that part to production, and ultimately the machine, they know what they're going to make it with. So that's one area where we see folks taking this technology to new heights. We as well see also an indirect approach where folks have, you know, legacy parts that they currently manufacture. May take a long time. They have to braze it. They have to do this, that, or the other thing. Where they want to do things additively. There's plenty of people getting in with that, but sometimes the ROI can be tough to find going that route. From a technical standpoint, you know, why do this at all? A lot of folks, they want to improve performance. They want to decrease weight. They want to optimize the product. You know, part consolidation is a big piece in all of this. And so reducing constraints on manufacturability is certainly a technical driver that we see often, as well as product optimization. From a business standpoint, you know, we see lots of customers able to open up the potential for new markets, as well as penetrate existing markets more deeply by being able to sell a component at a higher price point than maybe they were prior. There's critical processes and critical path. We have many folks who really get their first taste of metal AM through the R&D development process, may it be for materials, the different machines, an application. But really, critical path is a different beast in that, you know, we can provide you materials and parameters for building a part. But really, when you take things to production, you know, you need that 15 or 20% to tweak surface roughness, porosity, these types of things to really take things to a much deeper level. And that's where we see folks with that are using this technology for critical path production, taking things further. Forgive me. Technical difficulties. Excuse me, folks. There we go. One example we have, this is from the Additive Manufacturing magazine, March of 2017. A group of engineers looked to redesign this turbine engine. You know, you can read the metrics there. This was just a case study. This actually did not take place, but we actually haven't done the full calculation. But I would think most of the folks in this room would agree that there's a significant opportunity here as it relates to the biggest one that gets missed by a lot of people is the supply chain. I know a lot of OEMs, both OEMs and tier one suppliers, this is really a critical place for them as in managing their supply chain, where they're looking to bring metal AM on into what they're doing. You know, again, as in aerospace, I mean, if we had to do a breakdown by industry, we have aerospace, energy, dental, medical, tooling, as well as automotive that are adopting this technology. when it relates to designing new, some key considerations is in your target application is the geometry, the material you're going to make with it, as well as supports. Again, designed for additive manufacturing, and really eliminating the manufacturability restrictions. Being able to build organic, swoopy shaped parts. I don't have a good example there, but your prismatic things, those aren't really good options to consider for metal AM. For selecting existing geometry, complexity certainly drives ROI, and are the materials that we have available a suitable substitute for an additive built part? These are, again, just some considerations. There's many things, many characteristics to take into account when approaching the critical questions that need to be asked as it relates to the technology. Again, high complexity, organic shapes, low quantity. Most folks, you can see with where they're taking production with having a digital inventory, tooling, and use parts, as well as then on an engineering standpoint, being able to develop new materials, launch a new product, or penetrate a new market with new geometry. Materials, you can go and plug and play available materials in stainless, tool steel, titanium, aluminum, cobalt, chrome, Inconel right now today for many of the major providers. This would be new materials are coming out constantly. The powder manufacturers are constantly introducing new powders. The additional option, one unique thing with our system, some others as well, is we do have open architecture in our machines, meaning you can go and find a third-party powder provider. You can get powder from them and receive parameters from us that are completely open that you can then change and manipulate on your own. We have software tools, again, on the peripheral side with the ability to allow you to iterate and find the best parameters for that material. That's where you see this image here. Each one of these cups you could make, you could do different parameters with to ultimately account for surface roughness, porosity, a variety of factors in that part. But that's really a big key in all this, is discovering and optimizing the parameters, especially as it relates to taking a part to production. You could use a rule formula-based parameter assignment to, again, identify those optimal parameter settings. These are the critical controls and parameters that we find in the powder bed fusion process. I won't read off the slide, but a big piece that folks don't consider that does need to be considered is gas flow. You can see sometimes you got to fall down to pick yourself back up. For us, this picture here, you can see a perforated wall, an air blade here, an air blade here. This actually keeps the lenses clean, as well as this helps with the coating of powder. Gas flow is a real important factor in making quality parts, as you need to remove that soot and smoke. And I could go into more detail, but I would just say that's a key consideration. As I mentioned earlier, people want to go faster and go bigger with this technology, but that's a key aspect that makes things difficult in scaling these machines. Metal integrity is also a key item to consider. We have some various tools to help with the quality monitoring, both with the powder delivery. We have a means in our layer control system where the machine does have some intuitiveness and the ability to auto-correct if it doesn't lay a sufficiently good layer of powder. It can, through grayscale images, understand that and try again. If it doesn't work a second time, it will actually stop the machine. That's one option. There's also some other things as it relates to both the melt pool and laser power that allows folks to, if you did have an issue or did have an anomaly in a build, it would give you insight or a reference point to understand that more deeply. There's more and more as it relates to the actual part quality that's coming forward. Again, we as an organization are trying to do more around training and certification to help with that, especially as folks take parts to production. For those of you who are unfamiliar, this is just there's that one. This is just an example of what the process looks like. So we actually have a machine, and for those of you who would like to see it live and firsthand, we actually have a machine here in the exhibit hall. This one's super cool with the, this is actually right at the powder bed. You know, we're really, this process and what makes it so difficult, I imagine lots of folks have experience or exposure with polymer-based additive manufacturing. What makes metal AM so difficult is, you know, we're trying to control chaos here. You got particles flying, you know, you got small powder size, small micron size powder with laser energy hitting that at a high speed. Again, you're trying to control chaos. So more and more we're finding, again, peripherals and other means to validate and confirm that we're getting a quality output. So. Here we go. There we are. So, you know, I say start with the RI, start with the value. This is just a typical backwards approach I take with customers. And let's look at the value. You know, you got to start somewhere. Let's talk about the application, the materials. They all interplay. They're all interconnected in really finding, do you have a good candidate for metal additive manufacturing? If applications are going to help you improve a product, penetrate a new market, reduce time and costs, and that's driven by the materials and how you're going to make it. You know, understanding that we don't have all the metals yet available, and that, you know, machines really do impact surface physics, precision, integrity of the part, and we also need the means to validate consistency and quality of those parts. Then you get into how big, how fast, and for us, this is the pitch part of the presentation. You know, we got small, medium, and large here. As I mentioned from the outset, one thing that we've been a pioneer in is the multiple lasers. That's really how you're able to scale this technology. It also is where it makes things difficult, as I mentioned, with the whole gas flow piece, but we do have available laser options in both 400 watt and 700 watt, but these are the machine offerings. This is consistent amongst all our systems. They're top fed, meaning gravity fed, where we are able to then have a bidirectional recoater. Layering time is a significant piece. It takes 8 seconds to lay a bed of powder, and so by being able to do so with a bidirectional recoater, you're able to save time in recoating. And on standardized lasers and optics, again, we have tools to make sure that as you scale up, should you start with one machine and graduate to another bigger machine, that your homework's done as it relates to both parameters, materials, things of that nature. You don't have to start from scratch and reinventing the wheel to achieve the same results as you did in maybe a smaller machine or a one laser option, something like that. Flexibility, open parameters set for you as the user, customization, as I mentioned, as it relates to production. It's that 15, you're going to want to kick the training wheels off, and it's that 15 to 20% of the process where you really want to tweak things in and hone things as it relates to the parameters. Safety, again, it's top fed. You know, the only exposure to open powder is really when the operator is adding it to the machine. Finally, we use a soft recoater. There are others that use hard. Reason that's big if you're doing some type of lattice structured part, then you wouldn't have issues with potential nick in the geometry as the recoater lays a bed of powder. I've mentioned the gas flow already, but that's again a key piece in all of this to consider as you explore the technology. I'll touch on this a little deeper on the monitoring options available. We have process sensor monitoring on every system. This takes a record or recording of all the machine variables as it relates to oxygen, ambience, lots of characteristics it takes a snapshot of every 2 to 3 seconds. This helps to verify consistent process conditions and gives you a reference point, as I mentioned, if you did have an issue in the build. We also have a layer control system, which is what I was alluding to earlier with the whole grayscale overlay. That verifies the integrity of each powder recoat prior to the scan. We have a couple additional peripherals that we're excited about. These are pretty new and recent. Laser power monitoring. This is here at the show with us, as well as melt pool monitoring. The laser power monitoring gives an accurate real-time reading of the laser power. If you did have a deviation in power, it would tell you that. Similar, the melt pool, it gives an actual thermal emission, or it captures a measurement of the thermal emission from the melt pool to, again, give you a reference point or insight into maybe something going awry. Where's all this headed? Who cares? We're just collecting data. Why is that meaningful? Well, the notion would be is that you would let all this be synchronized and aggregate that so the machine could self-correct and be able to understand or stop and pause a build should it need to, or correct and continue on. Wrong way. For us, again, this is the sales pitch of it. We were the first to introduce a fiber laser, first to process titanium and aluminum. And so we've been an innovator in this technology since the mid-90s, so it's not like it's brand new. It may seem that way, but it's not. Again, I mentioned the closed loop systems. That's certainly friendly to you in that everything's under an inert gas environment. It allows for the operator not to be exposed to metal powders. Finally, it gives you flexibility with trying various materials. We got folks all the time adding new stuff as it relates to the various powders. Finally, in the almighty dollar, more parts produced for each dollar spent on AM machine. That's, again, through the bidirectional recoating as well as multi-laser scanning. So a couple sample case studies. A lot of folks, this is a big one where if you looked at the part on the outside, it'd be pretty boring, but the inside's got a lot going on. That's certainly a successful use case we've seen. This was done on a twin laser, which is our small, medium, large. It's our medium machine. Integrated temperature channel without support structure. This part was designed with additive in mind, so this was a direct application approach. We also then have the organic, very organic door mechanism here. As it relates, I said aerospace was a key industry for us. We all don't want to pay more for flights or for air travel, both business and as personal consumers. So obviously the aerospace industry is looking for ways to optimize weight. This was something we worked on where this was a actuation mechanism. They used topology optimization software to derive this part. Yeah, it's very organic, very unique. This never went to production, I don't believe, but still gives you good insight into options that are available as it relates to the technology. Finally, this was a casting, so this is a big part. This was done on our largest machine. They were doing weight optimization, but this is an automotive. So it's a very big part. Again, they were able to achieve 30% weight reduction through using metal AM. In an indirect approach, this customer here actually took a legacy part and actually conventionally built that part of the. This was done conventionally, and then the remainder was done additive. We actually this part was put into the SLM machine to then have those features built. Kind of a unique application. We don't see it that often, but it is possible. So just another use case example for what it is. That's all I had for you guys today. Is there any questions? And there we are.
What booth can you see this live in, Graham?
Pardon me?
What booth number can you see the machine running live in? 1269.
1269, thank you. Like she said. Guys, forgive me, with the actuators or whatever I'm hearing, it's quite hard to speak. And anyway.
The question is about if you get two small parts, can you weld them together? Or let's say you have the smallest machine, 5x5.
Yeah. So the process is actually we're micro welding is what we're doing with the lasers. So it's that's what we're actually doing. So you could build two parts inside the build chamber. Yes, if you did have a part and you wanted to do like I showed you with the last part there in the case studies, you could do something like that. But are you looking to like fuse two parts together? Yeah. So the three criteria as it relates to materials, it's a great question. The material needs to be weldable. The next is, can that material be atomized or be able to be a good spherical quality so that it will flow through the machine. The final piece is low moisture. That's really kind of the criteria we look for as it relates to the materials. So if you have those things, we as an open system, you can run the material. The only challenge in that and the piece that would take some time and effort is the parameters. So being able to, if we have a close parameter, we can provide that to you, and then we can kind of go and tweak that. But that would probably take a little bit of effort and diving in on. So great question. Any others? No? Okay. Thank you, folks. Appreciate it.